Hey folks, Mr. Holderman here. We're going to take you on a brief tour of the history of the atom, which I like a lot because it tracks pretty well how you learn about the atom, both through your educational history and through this chemistry class. We start simple and we get more complex. So let's first talk about what a model is. And we're talking about a scientific model here. A scientific model is an attempt to understand or explain things. So we use models to try to simplify a lot of things. We usually try to simplify those things that are really big or really small. So obviously, as humans, we can't take in the entire universe, so we make a model of it, and it spins around in a little circle. Or model of the atom, like we're going to talk about today, because it's so small that we can't see it, so we blow it up to a life-size model so that we can see how it interacts. But unfortunately, all models fall short of reality because we have to either simplify them because they're so big or stretch them and expand them so that we can understand them if they're too small. But over time, models become more complex. Now, why do you think this is? So as we just talked about, when you were a kid, you learned about maybe the model of the atom is just a little ball. And then as you're learning more and more through your science classes, you learn more and more about the atom. So why do we think this is? Because we know more information. This is exactly what happens through the history of the atom, because many, many years ago, as we'll see, we didn't know a lot about it, and now we do. So that's the key idea as we gain more information. So keep that in mind as we go through these different models. So let's go back, rewind the clock. 2000-ish years ago, we had this guy, Democritus. And Democritus was credited for the first belief that atoms existed. So he had the first atomic theory, the first model. Now, it definitely wasn't like we know now, but he said that if you divide something in half, and then divide it in half, and divide it in half, and keep doing that, eventually you'll get to this thing that is indivisible, which is where the name atom comes from, atomos, which means it's indivisible or uncuttable. But he was a philosopher. He did not have any proof. He just thought about this and philosophized. No evidence. And Aristotle, a contemporary of his, didn't believe in atoms. So since he was so influential, unfortunately, that set us back 2,000 years. The one thing about Aristotle is that he was an empiricist. So let's take a look at him. There he is, good looking guy. He's an empiricist, so he believed that things were true based on your experience. And so they would talk about these, and again, they're not really scientists in the sense that we think of, but he said if you experience something, that's the only way to know if something is true or not. So kind of the foundation of scientific labs and experiments and things like that. So here we have Plato and Aristotle, and they just philosophize and talk about their views on the world in these big parties like this. So no labs being done here. But then comes along some actual evidence. We have to fast forward about 2,000 years. We get to this guy, Antoine Lavoisier, and he is often called the father of modern chemistry. He lived in the 1700s, late 1700s, and he developed and understood a lot of things about chemistry, but one of the most famous things he's credited for is the law of conservation of mass, which we've learned about. But that says that whatever we have before in a reaction has to be whatever the amount that we have after the reaction. So the mass before equals the mass after. And they didn't really know anything more than that at this point. So while now we have this chemical equation, might look something like this, they didn't know what all of this stuff was. They just said, here's some mass, because they can measure that. Here's some mass afterward. We know that these two things have to be equal. They don't lose anything. We don't go anywhere. But they talked about it as a broad property. They didn't talk about the individual particles. So if we have 5 grams of the starting thing, we have to have 5 grams of the thing at the end. Then, based on that, so we're getting more and more complex. Based on that, we have this guy, Joseph Proust. So in 1797, he came up with the law of definite proportions. And what that said was that each chemical compound has a fixed and unchangeable ratio of the weights of the elements. So again, building off of the first model, we developed this law of definite proportions. So we know that not only do we have the same mass before and after, but if we have a compound, we have to have the same relative weights of the different components. So he worked a lot with copper carbonate, And copper carbonate is made up of copper, carbon, and oxygen. And so he didn't know about the chemical formula like we would now, but he said that whenever we see copper carbonate, about 50% of it is copper, 10% of it is carbon, and about 40% is oxygen. So then based on that, this is just 6 years later, John Dalton comes around and he puts kind of all of these ideas together, and he does some experiments in his own right, but comes up with the first real atomic theory. And there were a few parts to this. So this may look a little bit different than on your worksheet. Just like the example, we had water versus copper carbonate. So just a little bit different, but same ideas. The atomic theory first principle was that all matter is composed of atoms which are indivisible and indestructible. So again, you can see where that idea came from. Initially from Democritus, and then later that was the very first piece that they based everything else on. Number two, all atoms of the same element are identical, and all atoms of different elements have different properties. So when we were drawing particle diagrams, same as we learned it first in chemistry class, we drew all of the elements the same. And then once we learned about different elements, we started shading one, having one like an open circle and dark circle to show that atoms were different based on their elements. Next principle is that compounds are composed of two or more different elements in a definite ratio. Now you all know the definition of compound, so that fits right in. And then in number four, in chemical reactions, atoms are combined or rearranged. So those last two are really building on Proust's idea of the definite ratio or the definite proportions. But now we're taking the idea of the indivisible little particle that was an atom and combining it into that theory. So a little bit more about him. This is the guy right there, and he loved to draw these particle diagrams. So I really like these, and I think these would be a great addition if we could put them in our particle diagrams. We see the basic elements that he drew at the top, and then if we were to make compounds, we have two or more different elements chemically combined. So exactly where we get those particle diagrams from John Dalton. In his model, he was the first to say that it is this tiny little thing that looks to us, our model is a marble. It doesn't have any parts. So if we break it into small enough bits, this is what it would be. So then we learn a little bit more. We know we have an atom, but now we're going to learn about the parts. So let's kick it over to Mr. Holderman, who's going to show us J.J. Thomson's experiment. Thanks, Mr. Holderman. So what we got here is J.J. Thomson's setup. This is a cathode ray tube. So if any of you are familiar with the old, they're called CRT, cathode ray tube TVs. Those are the big ones that take up about this much space, definitely not flat screen. They're the same setup. We see, if you can see a faint line going across there. So what it's doing is shooting electrons from one side to the other. And of course, they didn't know this at the time. That's what they were coming up with. But there's a plate in between it. So it's phosphorescent. When the electrons hit that plate, they light up as that green line that we see going across. So here I've got a magnet, and when we bring a magnet close to it, it's kind of the same as a charged plate in his example, we can make that line dance. So if I bring the negative end of the magnet up to it, it's going to repel the electrons, so they start shooting down toward the other end. If I bring the positive end toward it, they pull them up off the screen. Send it back to Mr. Holderman, teach you a little bit more. Thanks, Mr. Holderman. So key things here for J.J. Thomson. He discovered the electron, and the way that he did that was with his cathode ray tube experiment. He put a stream of particles in between two charged plates, which you can see in the picture. And those particles were deflected away from the negatively charged place, so they must also have a negative charge because they know negative charges repel each other. He did not call these electrons, he called them corpuscles. So we have protons, neutrons, and corpuscles. Wouldn't that be funny now if we called them that? I like electrons, but that's what he discovered. So now we have one part. And his model built on that. So we can see the similarities to Dalton's model, where we have this ball, but now we know there are electrons, and they're really, really tiny. So we have to put the electrons in there. And the problem with that is that they're negatively charged, and we have to have something to balance them. So he said that the tiny little negative charges have to be built in this like pudding of positive charge. And he was English, so they had plum pudding, and the plums were the electrons, the pudding was like the cakey stuff, and it was just a positively charged medium. This would be like a fruit cake or something in America. So based on that, if your understanding is that we have these tiny little particles, we get this guy Rutherford, and Rutherford was one of J.J. Thomson's students, and he came up with this gold foil experiment. So the setup, which we're going to look at in just a second, is that he fired alpha particles at a thin sheet of gold and observed what happens. An alpha particle, they didn't know about protons and neutrons at the time, but an alpha particle has 2 protons, 2 neutrons, and it has a positive charge. So this is the setup. They have a lead box, and they're shooting this stream of alpha particles, and this is the gold foil. And then there's this detector, just like the detector in J.J. Thomson's experiment. And so based on where these alpha particles hit, that detector lights up. So we're going to take a look at that experiment, and you get a chance to be Rutherford in this next one. So with this PhET simulation, we've got Rutherford's gold foil experiment, and you're more than welcome to go on to PhET, use the link, and practice all of these for yourself. But I'm going to walk through all of the questions up to the CER so you know what the experiment looks like. So we're going to start with the plum pudding atom. And let's see, we want to set the alpha particles to the max so we can see the particles going through. So this is our setup. We're looking at it from the top view. So we're going to shoot alpha particles at this gold foil there. And then when we're ready, we just shoot particles. So this is the alpha particles coming through at a beam, and this is what it would look like. Now, so we assume that we are J.J. Thomson because that's the current model that we understand. And this is if J.J. Thomson's model were correct. We have all of these little tiny electrons in this generally positively charged little, that's the pudding part. So if that were the case, this is what we would see. So what happens to most of the alpha particles? Well, they're just kind of shooting right through there. Now, let's check out what actually happens with the Rutherford atom. So this is the same setup. We're going to turn the alpha particles up to max, and we've got gold with 79 protons. And if we shoot the alpha particles, what actually does happen? Let's turn on traces so we can see where they're going. So all of these alpha particles are shooting at the gold foil, and instead of going straight through, we see that some of them get a little bit deflected. Ooh, look at that one. It gets right turned around. But some of them, as they get close to what we know as the nucleus, they get deflected or bounce around. So the plum pudding to the Rutherford. We assumed that they would all just go straight through and not interact with anything, but they do. And we know that these alpha particles are pretty massive. You know, they've got some heft to them, 2 protons, 2 neutrons. So the only way for them to get deflected would be if there's something there to run into, which they didn't know at the time. So if we zoom in a little bit, we got the single nucleus option. We can see that they don't actually hit the nucleus, but we know that the positively charged alpha particles get close to it. Now, why would they be repelled? Well, what do we know about the charges? We know alpha particles are positively charged, and a nucleus is also positively charged. So when they get close, they just repel each other. And going back to our setup here, if we want to change the number of protons, we can change it to anything that we want. We can change it to, let me stop the alpha particles shooting across. We can change it to gold with 79 protons. We can change it anywhere from 20 to 100 protons. So if we were to do this, we want to change it to silver. So a couple questions for you. What would we have to change the slider to? How many protons would silver have? It's a nice review question for you. And then the CER that you get to answer is this. If Rutherford had fired alpha particles at silver foil instead of gold foil, would he have drawn the same conclusions from his experiment? So you get to answer this in CER format. A couple of things to help you. Think through what the major understanding was. We thought it was going to be this plum pudding thing, So would we have come up with the same experimental results with gold particles as if we were to have silver particles? What are the major differences there?